The moon today drifts quietly through the night, serene and predictable. Its pale glow feels eternal, as if it has always hovered at that same distance, that same size, that same slow rhythm of rising and falling. But the sky we know is only a snapshot, a peaceful moment in an ancient story filled with chaos, fire, and unimaginable closeness. There was a time when the moon towered above the world, so large it filled half the sky. Tides rose hundreds of meters. Nights never fully darkened. The earth spun like a top, and the sky was a theater of violent forces sculpting the world we now take for granted. This script explores that forgotten era, one section at a time, moving gently, calmly, through the science of a past that feels mythological, yet is entirely real. No section will repeat the previous. Each will explore a new phenomenon of the early Earth-Moon system, the origin of the moon, the roaring tides, the bright nights, the rapid rotation of Earth, the molten surface, and the slow drift that continues even now. Let us begin with the beginning, with a world newly formed and a moon so close you could almost feel its pull. Section 1. The Moon's Birth, a collision that changed everything. To imagine the moon's earliest days, we must return over 4.5 billion years to a time when the solar system was young, crowded, and violent. The planets we recognize today were still gathering mass, sweeping up dust and rock, colliding with smaller bodies, and occasionally encountering something far larger. Among these encounters was one that would alter Earth forever. Scientists call it Theia, a Mars-sized body in an unstable orbit that crossed Earth's path. For millions of years, Theia drifted closer, nudged by gravitational interactions with other forming planets. And then, with catastrophic precision, it struck Earth. This was not a gentle merging. The collision released energy beyond imagination, enough to vaporize rock, melt half the planet's surface, and fling a glowing spray of molten Earth into space. For a moment that likely lasted only hours, Earth was surrounded by a ring of incandescent debris, swirling and shimmering like a newborn Saturn. From this fiery ring, the moon condensed. Tiny droplets of molten rock cooled into larger clumps. Clumps collided into boulders. Boulders smashed together into moonlets. Each impact released heat, shaping the surface of the forming body. Gradually, through gravity's tireless pull, these fragments coalesced into a sphere, the early moon, still molten, still glowing, but whole. In this era, the moon was astonishingly close to Earth, just 20,000 to 30,000 kilometers away, compared to its current distance of 384,000 kilometers. Imagine looking up into the sky and seeing a moon 10 to 20 times larger in diameter, dominating not just the night, but even the day. Its surface, still volcanic and unstable, would have reflected sunlight like a polished ember. The young moon may have glowed red or orange, its heat creating a shimmering halo. And Earth, too, was different. The surface was a global ocean of magma, churning, boiling, reshaping its crust again and again. Volcanoes erupted from fissures in the newly formed crust. Meteorites continued to fall, adding new scars to a world already wounded by collision. The sky may have been hazy with rock vapor and dust, illuminated from above by the luminous sphere of the moon. The early moon orbited rapidly. Instead of taking 27 days to circle Earth, as it does now, the young moon completed an orbit in only a few hours. This meant that in the span of a single day, the moon might rise and set multiple times, each pass creating monstrous tides that reshaped Earth's waters and molten surface. But even amid this violence, the system began to stabilize. Earth's rotation slowed slightly with each passing year. The moon drifted outward at an incredible rate, dozens of centimeters, even meters per year. As it moved away, its orbit lengthened, the tides weakened, the world cooled, and the fiery glow faded. The striking thing about this period is how quickly chaos gave way to balance. Within tens of millions of years, a blink on geologic timescales, the magma oceans began to solidify, the atmosphere began to change, and the moon settled into a more familiar rhythm. But the memory of that ancient violence remains locked in the chemistry of lunar rocks and the tilt of Earth's axis. When astronauts brought samples back from the moon, scientists found something astonishing. The rocks were nearly identical in composition to Earth's outer layers. This provided the smoking gun. The moon was not captured. It was not formed elsewhere. It was born from Earth itself. The moon is, in a sense, Earth's child, a fragment flung into space that returned as a permanent companion. This connection explains why the moon influences us so deeply, from our tides to our climate to our sense of time. Without the moon's stabilizing influence, Earth's axis would wobble wildly, producing extreme climate swings. Life may never have evolved as it did. The moon, born from a moment of destruction, became a guardian of long-term stability. And yet, in that earliest era, stability was unimaginable. The night sky was a scene of molten fire, towering tides, and a moon so close it filled the horizon. It was a time when destruction and creation were inseparable, when the violence of cosmic formation created the conditions for future calm. This was the beginning of our night sky's story, a calm glow after a violent beginning. Today the moon drifts away from us at the slow pace of a fingernail's growth. Each year, the night sky becomes a little emptier, a little quieter as the moon retreats. It is impossible to see this change directly, yet knowing it is happening adds a gentle poignancy to every moonrise. The moon began as a blazing, violent beacon in the sky. Now it is a soft light, steady, comforting, familiar. Its journey from fiery birth to tranquil presence mirrors the cooling of Earth itself, and perhaps even the maturing of humanity's own perceptions. As we explore its past, we rediscover our own, our planet's chaos, its resilience, and the strange partnership between Earth and its unlikely companion. A world once torn apart became a world capable of life, under the watch of a moon slowly stepping back, leaving space for calm. Section 2. Tides of Titans, when ancient oceans rose like mountains. Imagine standing on the shore of an ancient Earth, one without continents shaped like today's, without familiar coastlines, without cities or forests, or even life larger than microscopic cells. Now imagine looking upward and seeing a moon so massive in the sky that it appears 20 times wider than the moon you know. Its gravitational pull would not only tug gently at the seas, it would lift entire oceans into vast, sweeping bulges, hundreds of meters high. These were the tides of the early Earth, and they were unlike anything that exists today. When the moon first formed, it orbited incredibly close to Earth, completing a full orbit in just a few hours. With every rotation, the moon's gravity stretched Earth's oceans into colossal tidal swells. These tides did not simply roll in and out. They thundered across the planet like slow-moving walls of water, reshaping coastlines and flooding vast stretches of land again and again. Every few hours, the ocean basins filled and emptied with the energy of global storms. To understand why these tides were so extreme, we need to consider the physics of gravitational interaction. The strength of a tide depends on distance. If the moon's current pull creates tidal ranges of 1 or 2 meters in many places, imagine what happened when it was 20 or 30 times closer. The force increases dramatically, not linearly, but exponentially. Even the crust of the Earth, not just the water, bulged under the moon's influence by tens or even hundreds of meters. The solid ground was pulled like soft clay under this enormous gravitational hand. The energy in these tides was unimaginable. As the tides surged, they generated titanic friction in the oceans and along the shorelines. Each rise and fall acted like a brake on Earth's rotation, gradually slowing the young planet down. In those early days, Earth spun so quickly that a full day lasted only 4 to 6 hours. Sunrise and sunset came and went rapidly, with the moon whipping around the planet several times each day. These cycles were frantic compared to the gentle 24-hour rhythm we experience now. But even more astonishing were the tidal waves generated inside the molten Earth itself. The early Earth was still partially liquid beneath a thin crust. The moon's gravitational pull kneaded the mantle like dough, causing the interior to swell and contract. This process heated the planet from within, keeping the mantle molten longer than it otherwise would have been. Without the moon, Earth's interior might have cooled more quickly, changing everything from volcanic activity to the formation of continents. Above the oceans, the tides influenced the atmosphere too. Air currents were dragged by the shifting seas. Winds roared across the early planet, driven not only by heat, but by the motion of the water beneath them. Storm patterns may have been drastically different, larger, and more chaotic, shaped by tides that rose and fell far faster than any modern hurricane cycle. Yet, despite their violence, these early tides played a crucial role in setting the stage for a stable planet. The tidal friction they created slowed Earth's spin, lengthening the day over millions of years. As the days grew longer, the moon drifted farther from the Earth, moving into a wider orbit at a pace far faster than today's slow drift of 3.8 centimeters per year. In those early eras, the moon may have receded by meters each year, rapidly transforming both the sky and the rhythms of Earth. As the moon moved outward, the tides began to calm. No longer did they rise like mountain ranges. They became smaller, more predictable, and far less destructive. Over time, the continents began to form more stable coastlines. The terrifying super tides that once flooded the planet instead became the gentle breathing of oceans we know today, a rhythmic inhale and exhale that has guided life for billions of years. Scientists believe that these powerful ancient tides may have been essential for the origin of life. As the oceans repeatedly surged onto land and then receded, shallow tidal pools formed, warm, mineral-rich basins that filled, evaporated, and refilled again and again. These environments concentrated organic molecules and provided the perfect setting for chemical reactions that could have sparked the earliest forms of life. The moon's enormous pull may have helped create the first steps toward biology itself. But in the time before life, the tides were nothing short of apocalyptic. If you could travel back to that era, you would see landscapes constantly reshaped by water. Islands might vanish beneath a rush of ocean, only to reappear hours later. The shore would never be still. The sound alone would be overwhelming. Imagine the roar of water, hundreds of meters deep, surging repeatedly against newly formed landmasses. Across the sky, the moon would dominate. It would appear so large and so bright that shadows would stretch sharply across the landscape even at night. You might see the moon's volcanic plains glowing faintly as molten rock still bubbled beneath its surface. Its cratered face, familiar to us now, had not yet fully formed. Instead, vast seas of magma hardened slowly as meteorites occasionally struck with dazzling flashes, and the tides responded instantly. A meteor strike on Earth or the moon could send waves across the oceans, amplified by the moon's immense gravity. The water systems of early Earth were never calm, never settled, never predictable. Over millions of years, however, the system quieted. A balance emerged. Earth's day grew longer. The moon drifted outward. The oceans stabilized. Volcanoes cooled. The once towering tides softened into gentle cycles. And the conditions for future life, stable climate, predictable seasons, calmer seas, slowly developed. When we stand on the shore today and watch the tide roll in, it feels almost serene. But hidden within that quiet motion is the memory of a world shaken and shaped by the moon's early embrace. A world where tides were titans, sculpting the young planet with the strength of oceans rising like mountains. Section 3. The Neon Night. How a closer moon made the nights glow. Imagine stepping outside at night, into a world where darkness never fully arrives. A world where the sky is washed not in black, but in a soft, silvery blue radiance, as though someone had placed a lantern the size of a continent just above Earth. This was the glow of the ancient moon when it hovered far closer to our planet than it does today. In those eras, nighttime was not a quiet retreat from the sun's brilliance, but a luminous performance shaped by Earth's celestial companion. To understand the ancient night sky, picture the moon appearing not as the modest disk we know, but as a giant sphere dominating nearly half the horizon. Its surface features, craters, fissures, plains of cooling lava, were so sharply visible that they would have appeared almost like mountain ranges within arm's reach. The light it cast was not the pale wash we experience today. Instead, it was bright enough to cast strong shadows, bright enough to reflect off oceans in shimmering sheets, bright enough to reveal details of the landscape as if illuminated by 1,000 lanterns. But the real magic came not just from brightness, it came from color. The early moon was geologically active. When it first formed, its surface was a glowing ocean of magma. Even after that molten sea cooled into solid crust, volcanic activity continued for millions of years. These massive lava flows released gases and created clouds of hot particles that sometimes spread thinly into the early lunar exosphere. When illuminated by sunlight, these particles could glow faintly, producing a delicate halo around the moon, similar to the pearly corona seen around the sun during an eclipse, but softer and more constant. On the early Earth, this halo may have made the moon look like a luminous orb surrounded by a mist of color. Blue-white at times, perhaps tinged with faint orange or red during volcanic outbursts. Nights would have felt otherworldly, as though Earth were orbiting within the glowing shell of a cosmic lantern. But brightness and color were only the beginning. The moon's closeness changed the very texture of night itself. When the moon was young and molten, heat radiated from its surface. Seen from Earth, this radiant heat, though not felt directly from such a distance, could create shimmering effects in the atmosphere, similar to the waviness you see over hot pavement. Starlight passing through the heated air near the horizon might have twinkled differently, producing nights full of distorted, dancing lights. The ancient Earth's atmosphere, thicker and more turbulent than today's, refracted moonlight in ways that might have made halos, arcs, and strange luminous patterns far more common. Imagine an early night sky painted with ethereal circles of ice crystal halos, only magnified by a moon that filled a huge portion of the heavens. The moon might have appeared with rings like Jupiter's, illusory rings created not by debris, but by Earth's own atmosphere refracting its intense glow. And then there were the nights of storms. In the early Earth, storms were more frequent, more intense, and more electrically active. Rising and falling tides churned the oceans and stirred the atmosphere. Volcanic activity heated surface areas and triggered immense weather systems. As storms built, moonlight intensified their appearance. Imagine lightning flashing across the world, illuminating giant waves raised by the moon's pull, while the moon itself cast a bright foreglow behind the storm clouds. The tops of storm towers, vast cumulonimbus giants that may have reached higher than anything today, would glow faintly from moonlight, reflecting off billions of droplets. In some eras, volcanic eruptions on Earth sent ash high into the atmosphere. That ash, in turn, refracted moonlight into surreal colors: deep reds, coppery oranges, or eerie greens. To an observer, the moon might have looked like a glowing ember suspended in a dust-filled night. This combination of storms, ash, and moonlight produced a nightscape that was constantly shifting, sometimes calm and silver, sometimes glowing in fiery hues. And when the moon passed behind Earth's shadow during an eclipse, the event would be breathtaking. The moon, already massive in the sky, would slowly darken, turning a deep blood red or even dark purple due to the thicker ancient atmosphere filtering sunlight. An eclipse in that era might have lasted longer, been brighter or darker depending on atmospheric conditions, and would have felt far more dramatic simply because of the moon's enormous apparent size. the whole sky would change color. Shadows would lengthen and then fade. Animals, if any existed, would have been confused. Even the ocean's surface would have changed appearance as moonlit waves suddenly sank into twilight. However, the most enchanting sight might have been something we can barely imagine: Earthshine on a closer moon. Earth, in its youth, was brighter than it is today. With more volcanic activity, glowing lava flows, and a thicker atmosphere reflecting sunlight, Earth shined intensely. That light illuminated the moon's dark side in a radiant glow known as Earthshine. From Earth, you would see not just the sunlit crescent of the moon, but also the rest of its surface, softly illuminated in bluish light reflected from Earth. It would feel as though the moon had two faces, one bright and sharp, the other ghostly and pale, both visible at the same time. This effect today is subtle. In ancient times, it was stunning. Earth's reflected light would have poured across the lunar surface, lighting up the moon in ways we cannot see anymore. The contrast between the moon's glowing crescent and its Earth-lit surface would have made it seem almost three-dimensional, like a sphere hanging close enough to touch. But all of this brightness carried consequences. Nighttime darkness was essential for many biological rhythms that evolved later. But early on, long before complex life formed, the brightness of the moon influenced Earth's chemistry. Moonlit nights helped shape temperature patterns, tides, and even the timing of volcanic eruptions. Over millions of years, as the moon drifted away, nights slowly darkened. This dimming allowed life to develop daily cycles, day for activity, night for rest, that remain woven into the biology of every living creature today. In other words, the ancient moonlit nights weren't just beautiful, they were foundational. They lit the early Earth with a cosmic glow, creating environmental rhythms that shaped the planet long before life rose from the oceans. And though that brilliant night sky is lost to time, its legacy lives on in the quiet sweep of the moon across our modern skies, a faint echo of a glow once bright enough to shift the world. Section 4. Earthquakes of the Ancient World. When the moon pulled at the planet's crust. Imagine a world where earthquakes do not arise solely from shifting plates underground, but also from the sky above. A world where the moon, looming enormous in ancient skies, exerts such a powerful gravitational pull that the very crust of Earth flexes, rises, and falls in response. Long before continents drifted into familiar shapes, long before forests or dinosaurs or oceans teeming with life, the early Earth trembled beneath the influence of the moon's immense gravity. These were not earthquakes as we know them today. They were tidal quakes, slow, rhythmic, planetary pulses driven by the moon's gravitational grip. To understand this phenomenon, think of Earth not as a solid rock, but as a layered, partially molten sphere. Beneath the crust, magma churned and rotated. Above this thin, fragile shell, the moon hovered far closer than it does now, perhaps only 15,000 to 20,000 miles away at certain stages, compared to today's average 238,000 miles. The gravitational difference was colossal. The moon's pull stretched Earth's crust like a taut rubber sheet, lifting massive regions of land upward, then releasing them. The result was a continuous cycle of rising and falling, like slow-motion breathing, except that this breath could crack continents. Ancient Earth's crust was young and hot. It had not yet thickened into the rigid plates we know in modern geology. Instead, it behaved more like a semi-flexible shell, floating on a deeper ocean of molten rock. When the moon approached during each orbit, the crust bulged upward by tens or even hundreds of meters. When the moon receded hours later, the bulge relaxed. This motion generated immense tension, enough to fracture surface rocks, trigger volcanic activity, and send deep rumbles across the world. These tidal quakes would have been predictable, not sudden jolts, but rolling waves of movement through the planet's surface. If you stood on early Earth, you might feel the ground shift beneath your feet, not violently, but with a slow, powerful heave, like standing on the deck of a ship as a distant wave passes under it. The noise may have been eerie, a low, resonant groaning as deep rock layers adjusted to the moon's pull. In places where the crust was especially thin, cracks might have opened and closed with each tidal cycle, releasing heat, steam, and gases into the air. These areas became hotspots for geological transformation. Volcanoes were common, not because of plate collisions like today, but because the moon's gravitational kneading forced magma upward. Each time the crust stretched, molten rock surged into fractures. The moon, in a sense, was stirring Earth's molten interior like a spoon moving through thick soup. In doing so, it kept Earth's mantle hotter for longer, slowing the planet's cooling and prolonging volcanic activity by millions of years. This tidal heating is not unique to Earth. We see it today in Jupiter's moon Io, a world covered in volcanic eruptions, constantly flexed by Jupiter's massive gravity. The same principle applied to early Earth, creating a geologically restless planet long before life emerged. But Earth had oceans, and this added another layer of drama. When the crust rose due to the moon's pull, so did the seabed. Vast quantities of water shifted with the rising land, amplifying the massive tides already driven by gravity alone. In some places, the seafloor may have risen so sharply that entire basins temporarily drained, only to flood again hours later as the crust settled. These cycles shaped coastlines, carved channels, and influenced the chemistry of the early oceans. The interaction between the flexing crust and moving water created spiraling currents of heat and minerals, conditions that many scientists believe may have played a role in the earliest biological chemistry. The tidal quakes may have produced underwater volcanic vents rich in nutrients, similar to the black smokers found today on the ocean floor. These vents pump out superheated water filled with minerals, forming the perfect environment for complex chemical reactions. In this sense, the moon did more than light the ancient sky. It may have stirred the oceans and crust in ways that helped life begin. But the moon's influence didn't stop at the crust. It extended deep into the mantle. Each time the moon's gravity stretched Earth, heat was generated inside the planet. This warming could have created pockets of molten rock, triggering eruptions, forming mountains, or collapsing underground chambers. Over time, the pattern of these tidal shifts may have helped shape early continental blocks. Where the crust weakened repeatedly, magma rose and solidified, building the foundations of future continents. Where the crust resisted, it remained as early proto-oceanic floor. This means that the moon may have played a central role in determining the early architecture of the planet, the first outlines of land and sea. The movement also influenced Earth's rotation. As the crust bulged and relaxed, frictional forces slowed the planet. A day lengthened by fractions of a second. Over millions of years, this added up to profoundly longer days. Each extra hour gave the early atmosphere more time to heat and cool, influencing wind patterns and climate cycles. The planet became more stable, more predictable, more suitable for life, and the moon, in turn, drifted farther away. As the moon receded, the tidal quakes gradually weakened. Earth's crust thickened and cooled. Geological activity shifted from moon-driven motions to the slow dance of plate tectonics. The massive, rhythmic flexing of the planet faded into the background, remembered only in the scars etched into ancient rocks. If we could observe those earliest quakes today, we might see patterns in the oldest minerals, tiny distortions hinting at a world once pulled like taffy by a nearby moon. These distortions are real. Scientists studying zircon crystals, more than 4 billion years old, have found chemical signatures indicating intense heating and cooling cycles consistent with tidal flexing. In other words, the moon left fingerprints inside the oldest minerals on Earth. Standing on early Earth, the experience would have been overwhelming. The ground rising beneath your feet, the air humming with heat and minerals, the moon looming huge overhead, pulling an entire planet like a puppeteer tugging strings. Volcanoes simmered, oceans surged, rocks cracked, and the world reshaped itself hour by hour. It was a restless, trembling world, but it was this very restlessness that prepared Earth for the calm stability we know today. The moon's ancient pull sculpted Earth from the inside out, turning a hot, chaotic young planet into a world with continents, oceans, tides, and eventually life. Without those early quakes, those planetary tremors driven by the sky, Earth may have been a colder, quieter, and far less hospitable place. The moon, even in its early violence, was a partner in creation. Section 5. The First Tides. When the oceans rose and fell like breathing giants. When the moon hung far larger in Earth's sky, so close that its light shimmered across the oceans with almost unnerving brilliance. The seas themselves behaved in ways that would feel alien to us today. Long before humanity existed, before continents drifted into their familiar shapes, the planet's waters moved with an intensity that sculpted coastlines, altered climates, and shaped the very rhythm of life. This is the story of those primal tides, Earth's earliest heartbeat, driven not by wind or storms, but by the gravitational pull of a moon that once hovered like a colossal lantern above the world. To understand why these ancient tides were so extraordinary, imagine the moon not as the quiet, distant companion we know now, but as a looming presence, filling a third of the sky. Its surface details visible even to the naked eye, its brightness almost enough to cast faint shadows. At that distance, its pull on Earth's oceans was several times stronger, tugging massive bulges of water across the surface of the planet. Today's tides lift water by a meter or two in most places, sometimes a bit more in extremes, but back then, tides could rise and fall by dozens of meters. Entire coastlines were swallowed and exposed twice a day, as if the oceans were breathing in deep, powerful cycles. These enormous tides didn't merely sculpt beaches and estuaries, they shaped entire ecosystems. Imagine primitive life evolving near the shoreline, simple organisms clinging to rocks, drifting in shallow pools, or nestling in soft sediments. Twice each day, they were lifted and carried far inland by surging tides, then pulled back toward the sea as the waters receded. This constant cycle of movement created countless small environments, tidal flats, rock pools, oxygen-rich shallows, and nutrient-drenched mixtures of land and sea. Many scientists believe that these shifting, unstable habitats were key in pushing life to adapt, diversify, and eventually transition toward land. In that sense, the moon, through its intimate gravitational dance, played a quiet but profound role in life's earliest evolutionary steps. But these tides did even more. They helped shape Earth's climate and weather systems. As giant waves swept across continents, they transferred enormous amounts of energy, generating early patterns of ocean circulation. Strong tides meant strong mixing. Warm surface waters churned with deeper, colder layers, preventing oceans from becoming stagnant or stratified. This mixing allowed for a more even distribution of temperatures and nutrients, which in turn supported life and moderated global climates. If the moon had been smaller or farther away from the start, Earth's climate might have evolved very differently and perhaps far less hospitably. The tides also influenced Earth's rotation. Every massive rush of water generated friction, tidal braking. Slowly but surely, over millions of years, this friction transferred angular momentum to the moon, pushing it farther away while gradually slowing Earth's spin. The result was a magnificent cosmic trade. The moon retreated, and Earth's days lengthened. From a chaotic early world with days shorter than 10 hours, the planet slowly drifted toward the 24-hour rhythm we know now. Without those intense ancient tides, Earth might still be spinning far faster, with rapid changes between day and night, and a far more extreme climate. Another remarkable consequence of these massive tides was their impact on geology. When water surges back and forth across coastlines with tremendous force, it erodes rock, carries sediment, and reshapes landscapes. In ancient times, this process would have occurred at a magnitude we can barely imagine. Huge bays carved into continents, mountains worn down, river deltas dismantled and rebuilt repeatedly. The coastline was not a stable boundary, but a dynamic, shifting frontier. Sometimes the tides reached dozens of kilometers inland, filling low-lying basins with seawater and leaving behind mineral-rich deposits as they receded. These deposits would later become layers of stone, fossil-bearing sediments, and even resources that modern humans mine and use. While all of this was happening on Earth, the moon itself was not idle. As tides pulled on our planet, Earth's gravity pulled back on the moon, slowing its rotation until it eventually became tidally locked. Today, the moon always shows us the same face, but in those early days, that was not the case. It spun faster then, revealing more of its mysterious surface. Slowly, over millions of years, its rotation stabilized, locking into the synchronous orbit we are familiar with. This process, too, was driven by the tides, those same colossal movements of water that shaped life and land. The beauty of this ancient Earth-Moon relationship is that it was dynamic, reciprocal, and essential. The tides weren't simply the result of proximity. They were the mechanism that governed the long, slow evolving dance between Earth and its companion. And in this dance, everything from geology to biology, from climate to the length of a day, was influenced. Imagine standing on such an early Earth shoreline, not as a human observer, but as an invisible witness. Twice each day, the ocean roars inland, filling valleys, swallowing forests of primitive vegetation, and surrounding rocky outcrops that moments before stood tall and dry. Hours later, the water retreats, leaving behind shimmering pools that reflect the massive moon above. The sky glows faintly blue-green with atmospheric haze, the air thick with moisture and early oxygen. Every tide is a transformative event, reshaping the world a little more. As the moon gradually moved outward, the tides weakened, becoming gentler, more familiar. The extreme tidal worlds faded into memory, buried in layers of stone, fossil, and the rhythms of life that adapted to more stable seas. But their influence never vanished. Even today, every wave that rises and falls is a gentle echo of the moon's ancient closeness, an echo of a time when the oceans were wild, the days were short, and Earth itself was still learning how to breathe. Section 6. The Age of Cosmic Impacts, when the moon shielded a young and fragile Earth. In the era when the moon hovered much closer to Earth, brighter, larger, and far more commanding in the night sky, our planet was still recovering from an age of heavy bombardment. The early solar system was a chaotic place, filled with wandering debris, leftover fragments from planet formation, shattered pieces of asteroids, and icy bodies migrating inward from the outer regions. Earth was a young world, struggling to stabilize, and the moon played a surprisingly protective role during this violent celestial chapter. To understand this period is to picture not just our shining satellite, but an enormous, crater-marked guardian whose presence helped shape the survival and evolution of life long before it even existed. When the moon first formed, likely from the debris of a cataclysmic collision between the infant Earth and a Mars-sized object, it was molten, glowing, and far closer to our planet than it is today. Its orbit was tight, its gravitational pull immense, and its size in the sky wasn't just visually dramatic, it physically influenced the space around Earth, altering the trajectories of incoming objects. A large nearby moon doesn't merely shine, it bends the paths of smaller bodies, subtly shifting impact probabilities. During the million-year period following its formation, the moon absorbed countless strikes that might otherwise have hit Earth. Each crater on the lunar surface is a silent memory of a meteor that never reached us. This was the age when both Earth and Moon were bombarded by leftover debris from the chaotic birth of the solar system. For Earth, many of these impacts were devastating, releasing energies equivalent to billions of nuclear explosions. Some boiled oceans, some vaporized large portions of the atmosphere. But the moon, locked in its close orbit, acted like a gravitational filter. Some incoming rocks were pulled toward it instead of Earth. Others were influenced just enough to miss both worlds entirely. This subtle gravitational guidance may sound small, but over hundreds of millions of years, it shaped the frequency and intensity of impacts that Earth experienced. To appreciate the moon's shielding effect, imagine a world without it. Planets like Mercury and Mars, lacking large nearby companions, bear the scars of countless impacts. Their surfaces are still pocked and jagged, reminders of ages in which celestial violence shaped their fates. Earth, in contrast, hides much of its impact history beneath oceans, tectonic shifts, and erosion. But even so, scientists estimate that the moon's presence reduced the total number of large Earth impacts by a significant margin. Fewer catastrophic collisions meant more stability, giving Earth time to cool, oceans time to form, and eventually, life time to emerge. During this ancient era, the moon itself was also evolving. Each incoming asteroid reshaped its surface, creating the vast basins we now call Maria, the dark, smooth plains visible even to the naked eye. Today these appear calm and silent, but they began as colossal wounds created by impacts so violent they melted lunar rock and filled entire regions with lava. These Maria were born during a time when the moon was still pulling away from Earth, slowly drifting outward, carving its long spiral into space. With each impact absorbed, its role as Earth's cosmic buffer became more deeply etched into its landscape. Meanwhile, life on Earth, still in its infancy, was profoundly affected by both impacts and the moon's protection. Early microbes and chemical precursors survived because the planet had long stretches without sterilizing collisions. While Earth certainly endured massive impacts, the absence of constant catastrophic bombardment allowed complex chemistry to flourish in warm pools, deep-sea vents, and tidal environments sculpted by the moon's gravity. In this way, the moon indirectly supported the emergence of life by reducing the frequency of global reset events. Another fascinating effect of the moon's closeness during this period was its influence on Earth's axial stability. Without the moon, Earth's tilt might change chaotically over time, like Mars, which wobbles dramatically, causing wild climate swings. But the moon's gravitational pull stabilized Earth, smoothing its tilt and giving the planet long-term climate patterns conducive to habitability. This stability meant that early life didn't face constant environmental upheaval. While impacts were still happening, the overall climate had predictable rhythms, light cycles, seasons, and tidal patterns, which formed the backdrop against which life could gradually evolve. The impacts that did reach Earth also played a role in shaping its future, though devastating. Some brought water-rich comets, delivering the essential ingredient for life. Others brought organic molecules, seeds of chemistry from deep space. Some created vast hydrothermal systems, hot, mineral-rich environments that may have been breeding grounds for early microbial life. In this delicate balance of violence and calm, the moon's stabilizing presence kept Earth from tipping too far toward chaos. Visualize the night sky during this ancient epoch. The moon glows enormous and molten, the air thick with volcanic haze from early tectonic activity. Occasionally, streaks of fire sweep overhead, meteors burning up or fragmenting as they approach the Earth-Moon system. Sometimes, you would witness a direct lunar strike, a burst of light on the moon's surface as an asteroid meets its end there instead of here. Each flash would be a moment of cosmic fortune, another potential catastrophe diverted. As time passed, the solar system calmed. Most of the loose debris was swept up or ejected. The moon cooled, its molten seas solidified, and its distance increased. The bombarded skies grew quieter, and Earth entered a more peaceful era. But the memory of that ancient protection remains inscribed in the moon's battered face. Every crater we see today is a reminder of the way Earth was shielded, protected by a satellite uniquely positioned to influence our planet's destiny. Even now, long after the era of heavy bombardment has ended, the moon continues to play a subtle but important role. It stabilizes our seasons, influences tides, and maintains the gentle rhythms that have shaped life for billions of years. It no longer shields us from impacts in the dramatic ways it once did, but its presence remains a reminder of our planet's delicate cosmic relationships. In this section of the story, the moon is not simply silent stone. It is an ancient guardian, a witness to the solar system's early violence, and a key reason Earth became a cradle for life, rather than just another scarred, barren world. Section 7. The moon's tides and Earth's early oceans. The rhythm that shaped life when the moon was far closer to Earth than it is today. Perhaps only a tenth of its current distance. Its gravitational influence on our oceans was immense. The tides it created weren't gentle rises and falls like the ones we see now. They were towering, sweeping forces that reshaped coastlines, stirred ancient seas, and set in motion rhythms that would eventually guide the evolution of life itself. To understand this era is to imagine a world where the moon's pull was powerful enough to sculpt the environment every single day, leaving a deep imprint not only on the oceans, but on biology, geology, and even Earth's climate. In the earliest chapters of Earth's history, the moon hovered overhead like a colossal glowing guardian, appearing many times larger in the sky. Its gravity pulled strongly on Earth's waters, creating tides that could rise hundreds of meters in some regions. These weren't gentle laps on a sandy beach. They were dynamic, forceful surges that swept across vast stretches of coastal land. The oceans themselves were still forming during this era, fed by volcanic outgassing, comet-delivered water, and the gradual cooling of Earth's molten surface. As these young oceans expanded, the moon's influence grew increasingly important. The most dramatic change caused by these ancient tides was the constant mixing of Earth's early seas. Today, tides help cycle nutrients between shallow waters and the deeper ocean. But in the distant past, this effect was on an entirely different scale. The enormous tidal forces churned the oceans like a planetary mixer, drawing up minerals from the seafloor and pulling them across coastal shelves. This mixing created chemically rich environments, where early life found the resources it needed to develop. Imagine standing on the young Earth's shoreline, if such a thing could even be called a shoreline. You might see vast tidal rivers gushing in and out with cyclical force. Pools formed and drained daily, leaving behind concentrated mixtures of minerals, salts, and organic molecules. These tidal pools were natural laboratories, warmed by the young sun during the day and exposed to starlight and lunar glow at night. They underwent constant cycles of wetting and drying, which scientists believe were crucial for forming early complex molecules like RNA. The moon's tidal influence also carved the first stable rhythms into Earth's surface. Before life could evolve biological clocks, the planet itself provided reliable timing. Twice a day, sometimes with terrifying grandeur, water surged inland, then retreated. Every creature that emerged later would inherit biological rhythms that echoed these ancient cycles. Even today, the circadian rhythms in every living thing, from humans to microscopic algae, bear the imprint of this ancient partnership between Earth and Moon. But tides didn't only shape the shallow waters. They also influenced deep-sea circulation. As the moon's gravitational pull tugged on the surface, it transmitted energy through the entire water column, setting up internal waves and currents that distributed heat around Earth. This circulation helped prevent the oceans from stratifying into stagnant layers, making the planet's climate more stable and uniform. Without this early circulation, the oceans might have become walked into hot, acidic surface waters and cold, dead bottoms, an environment far less friendly to evolving life. Another fascinating effect of the moon's closeness was its impact on day length. In the early days of Earth, a full rotation might have taken only 6 hours. The tides generated by the moon acted like a brake on this rapid spin, slowing Earth's rotation over hundreds of millions of years. Each massive tidal cycle drained a tiny bit of rotational energy, transferring it to the moon and causing it to drift outward. This gradual slowing gave Earth longer and more stable days and nights, a pattern of light that life would eventually adapt to and depend on. Life's earliest organisms thrived in coastal regions precisely because they were forced to adapt to constant tidal changes. The first microbial mats grew on surfaces that were sometimes submerged, sometimes exposed. These fluctuations encouraged cellular adaptation, resilience, and the innovation of protective membranes. Tidal stresses likely pushed early life to form communities that clung together for stability, setting the foundation for the first simple ecosystems. As life advanced beyond simple molecules into early single-celled organisms, these tidal zones became evolutionary hotspots. Constant environmental change created a powerful selective pressure. Only the strongest, most adaptable structures and behaviors survived. Some organisms began forming protective shells. Others developed motility to seek food or escape drying pools. Over time, the boundary between ocean and land, shaped by tides, became the stage for some of our planet's most significant evolutionary leaps. Even after the moon began drifting farther away, its tidal influence remained crucial. The tides moderated as the moon receded, becoming gentler, more rhythmic. This shift created broad coastal wetlands, environments that later became nurseries for more complex life. The first plants to colonize land, the earliest amphibians, and countless other species all relied on these transitional environments made possible by the moon's pull. Today, when we watch a tide roll lazily toward the shore, we're glimpsing a faint echo of an ancient force that was once unimaginably powerful. We see stability where there was once chaos, but that chaos was creative, not destructive. It provided the conditions for life to arise, evolve, and diversify. Without the moon's early tides, life on Earth might never have begun, or at least not in the same way. The tides provided the physical cycles, chemical concentrations, and environmental pressures that turned an ocean of possibilities into the first sparks of life. In this sense, the moon wasn't just a silent companion in the sky. It was a sculptor, a catalyst, and a timing mechanism. It shaped the chemistry of oceans, the rhythms of life, and the eventual habitability of the entire planet. Section 8. The moon's influence on early life, how a violent past became the cradle of biology. Life on Earth did not begin in calm waters, nor in quiet, undisturbed lagoons. It began in a world shaped by constant motion, a world where the moon, much closer and brighter than it is today, pulled relentlessly on Earth's oceans. This powerful gravitational interaction did far more than sculpt tides and carve coastlines. It created the environmental patterns that would become the earliest stage on which life could arise. To understand how deeply the moon shaped biology is to see that our evolution is intertwined with its presence, not metaphorically, but physically, chemically, and rhythmically. In the earliest ages, when Earth's surface was still settling from the chaos of its violent formation, the moon hung in the sky like a massive, glowing beacon. It may have appeared 10 or even 20 times larger than it does now. Its gravitational pull was overwhelming, far stronger than anything modern humans have experienced. Every day, enormous tidal waves surged and retreated across continents that were still forming, generating cycles of flooding and drying unlike anything on our world today. These cycles created the first natural laboratories. As the tides retreated, they left behind shallow pools filled with concentrated minerals, organic molecules, and chemical building blocks. The sun baked these pools during the day, causing water to evaporate and concentrate the remaining molecules further. When night fell, temperatures dropped and the pools cooled. The next tide surged in, refilling the pools and stirring their contents, allowing new combinations to form. This repetitive pattern, wet, dry, warm, cool, flooded, drained, may have been the key to assembling the first self-replicating molecules. Many scientists believe that life's earliest chemical steps required precisely this kind of cyclical environment. Molecules could form under one condition, break apart under another, rearrange, recombine, and gradually grow more complex. The moon's tides were not merely background forces. They were active participants in the birth of biology. Life's earliest building blocks, such as nucleotides and amino acids, likely benefited from the concentration created by repeated evaporation. In deep oceans, these molecules would have been too diluted to interact efficiently, but in tidal pools, their concentrations could soar to levels ideal for chemical bonding. Early Earth did not have the luxury of modern enzymes or complex catalysts. So, Physical processes like heating, cooling, and evaporation provided the energy needed to drive chemical reactions forward. As these molecules became more sophisticated, forming longer chains of RNA-like structures, they would have needed protection from harsh ultraviolet sunlight. The first forms of self-replication may have occurred under thin layers of water or beneath mineral surfaces. Interestingly, tides constantly reshaped coastal sediments, burying some molecules and exposing others, offering natural cycles of protection and exposure. Again, the moon's gravitational rhythm played a role in selecting which chemical systems survived. Once simple cell-like structures emerged, the moon continued to shape their environment. Primitive life bloomed in tidal zones, regions that were neither fully ocean nor fully land. These areas experienced constant stress, competition, and adaptation. Organisms had to survive changes in salinity, temperature, oxygen availability, and exposure to sunlight. These challenges became evolutionary pressure points, pushing early life to develop adaptability and resilience. The moon also indirectly influenced the chemistry of early oceans. Its tidal mixing churned vast amounts of water, bringing nutrients from the deep up to the surface, and circulating oxygen produced by early photosynthetic organisms. Without this mixing, surface waters might have become nutrient-poor and stagnant, slowing evolution dramatically. Instead, Earth's oceans were dynamic, oxygenated, and chemically rich, an environment in which life could diversify. Perhaps the most profound connection between the moon and living organisms is the development of biological rhythms. Long before complex organisms existed, life responded to predictable environmental cycles. The tides created reliable patterns: high tide, low tide, daylight, darkness. These cycles taught early life to count time. Many of today's marine organisms still follow tidal rhythms, carrying ancient patterns encoded in their DNA. But even terrestrial life, including humans, retains remnants of that ancient timing. The circadian rhythm, the roughly 24-hour cycle that governs sleep, hormone release, and metabolism, may have evolved from an earlier tidal rhythm shaped by the moon. Even though the moon's influence on our daily cycles is subtle now, the biological clock may still carry the signature of a time when tides governed everything. As life evolved, the moon continued to set boundaries and opportunities. The first multicellular organisms likely thrived in shallow coastal environments shaped by tidal forces. The daily mixing of water brought nutrients, oxygen, and sunlight into the perfect balance. Later, the first creatures to explore land, early plants, algae, and eventually animals, originated in these transition zones. Without tides, Earth might never have developed these fertile, dynamic environments. The moon's retreat over millions of years also influenced evolution. As the moon moved farther away, tides became more modest and predictable. This shift created stable ecosystems such as tidal flats, estuaries, and coastal wetlands. These areas became biodiversity hotspots, nurturing countless species that would later populate deeper seas and eventually terrestrial environments. In a very real sense, the moon acted as a gentle mentor for life on Earth. It began with violent, forceful tides that stirred chemistry into existence. Then, over billions of years, it calmed, offering predictable rhythms that life could depend on. It shaped climate, currents, ecosystems, and evolutionary pathways. Even today, many species rely on lunar cycles for reproduction. Corals, for instance, spawn based on the full moon, synchronizing the release of millions of eggs and sperm across vast distances. Sea turtles return to beach sands lit by moonlight to lay their eggs. Many fish migrate in harmony with lunar phases. The moon still whispers through the oceans, guiding life in ways that remain ancient and profound. And we too, even as modern humans, are quietly influenced by the moon's rhythms. Our tides breathe in and out. Our sleep patterns shift with moonlight. Our earliest stories, calendars, and rituals were shaped by the moon's glow. Life on Earth did not simply evolve under the sun. It evolved under two celestial influences: the daily light of the sun and the rhythmic pull of the moon. And while the sun provided energy, the moon provided structure. Section 9. When the moon was a sculptor. How its gravity reshaped Earth's crust and continents. When we imagine the moon shaping Earth, we usually think of tides, gentle waves, rising seas, and rhythmic coastal patterns. But in the ancient past, when the moon loomed massive and brilliant in a much closer orbit, its pull did far more than stir oceans. It tugged on the very crust of our planet. The early Earth was a world of molten rock, shifting plates, and unstable continents. And the moon, with its immense gravitational pull, pressed its influence into the land just as profoundly as it did into the sea. To picture this era, we must imagine an Earth that was still partially molten, wrapped in oceans of lava rather than water. The crust was thin and fragile. Continents, if they existed at all, were small prototypical landmasses rising briefly before sinking back into the molten mantle below. Into this unstable landscape, the moon pulled and pressed with tremendous force. Geological tides, similar to ocean tides but involving solid rock, swept through the crust every day as Earth rotated beneath its moon. Even today, the moon lifts Earth's solid surface by about 30 centimeters with every orbit. That is with our moon at its current, much greater distance. Imagine the effect when the moon was 10 times closer and hundreds of times more gravitationally disruptive. Entire regions of Earth's crust may have risen and fallen by several meters. These slow, powerful flexings produced cracks, fissures, and zones of intense pressure. They guided the early formation of tectonic plates and influenced where volcanic hotspots emerged. In the distant past, volcanic activity was not merely common, it was overwhelming. Earth was shedding its internal heat, and the moon's constant tidal tug acted like the stirring of a pot. By pulling on the partially molten mantle, the moon kept it moving and churning, preventing it from settling. This churning helped create the first large convection currents, the slow-moving streams of hot rock within Earth that drive plate tectonics today. Without this early gravitational stirring, Earth's crust might have cooled more uniformly, producing a stagnant shell rather than a dynamic surface. The moon's influence helped keep Earth geologically alive. It encouraged volcanism, mountain building, and continental drift. These processes were essential for creating the varied environments that life would later need. Earth's atmosphere, for example, was heavily shaped by volcanic outgassing. Gases like carbon dioxide, water vapor, methane, and nitrogen were released during enormous eruptions. These gases formed the early atmosphere, creating the conditions that allowed oceans to condense. And it was the moon's gravitational influence that kept volcanism vigorous. As Earth cooled, true continents began to form, rigid landmasses carried along by tectonic plates. But the moon's pull did not stop influencing them. In certain regions, geological tides focused stress along fault lines, encouraging some sections of the crust to fracture. These fractures became the boundaries of plates. Over time, these boundaries grew into the global tectonic system we know today. The mid-ocean ridges, the subduction zones, the transform faults that drive earthquakes and build mountains. Interestingly, the moon may have helped determine the locations of Earth's earliest supercontinents. As plates drifted, subtle resonances formed between Earth's rotation, the tides, and the movement of tectonic plates. These subtle gravitational harmonics, though faint, could guide where landmasses converged or separated. Long before Pangaea existed, the moon was nudging Earth's plates toward their eventual configurations. It is possible that the first supercontinent, Volbera, formed in part due to tidal stresses amplified over millions of years. But the moon's influence wasn't purely destructive or chaotic. It also provided stability. Planetary scientists believe that the moon's steady gravitational presence helped prevent Earth's axis from wobbling excessively. This stability was vital for the long-term climate, ensuring that Earth did not experience wild, frequent shifts between extreme hot and cold states. Without this balance, continents might have remained barren and inhospitable for far longer. As continents thickened and cooled, the interior of the planet continued to change under the moon's influence. Tidal heating, while minor compared to deep radioactive reactions, kept Earth's core slightly agitated. This agitation helped drive the geodynamo, the mechanism that generates Earth's magnetic field, and Earth's magnetic field, in turn, protected life from harmful solar and cosmic radiation. It shielded the atmosphere from being stripped away by solar winds, allowing life to flourish. In this indirect but profound way, the moon contributed to making Earth habitable. Another striking possibility is that the moon's gravity influenced the formation of early ocean basins. As Earth's crust rose and fell, some regions became naturally depressed, forming proto-oceans. When water condensed and pooled, these depressions deepened under the weight of the moon's pull, reinforcing their shapes. This process may have helped define Earth's earliest coastlines and the distribution of land and sea. Even in modern times, we can observe the subtle dance between Earth and Moon in geological records. Layers of sedimentary rock contain rhythmic patterns, tiny variations in layer thickness or composition that reflect ancient tidal cycles. By analyzing these layers, scientists can determine how fast the Earth once rotated and how close the Moon used to be. Each rock stratum becomes a fossilized record of the moon's geological handshake with Earth. As the moon slowly drifted outward, its influence on Earth's crust gradually weakened. Tidal forces became more modest, geological tides diminished, and Earth's continents stabilized. Yet the echoes of the moon's early sculpting remain. The arrangement of plates, the volcanism that forged the atmosphere, the deep ocean basins, the magnetic field, and even the climate stability necessary for life. All these, in some way, carry the moon's imprint. When we look up at the moon today, a small, quiet orb glowing in the night sky, it is easy to forget that it was once a titan of geological power. It flexed our crust, carved our oceans, stirred our mantle, and nudged continents across the planet. It helped turn a molten sphere into a living world. Section 10. Lunar Light and the Birth of Nighttime Life. How a bright moon shaped behavior long before humans walked the earth. Long before forests and grasslands covered continents, and even before complex animals existed, the moon hung close and luminous in the sky. Its light was extraordinary, bright enough to cast shadows at night, to illuminate the oceans, and to paint landscapes with a silver glow, unlike anything modern humans experience. This wasn't merely a spectacular visual phenomenon. It had profound consequences for the earliest nocturnal environments and the behaviors of emerging life forms. The moon's proximity amplified the reflection of the sun's light, making nights far less dark than they are today. In many regions, it could provide the equivalent of modern twilight or even early evening sunlight. On ancient Earth, with its shorter days, the cycle of light and darkness was intense. But the moon's brightness softened and regulated night. Life, in turn, began to evolve in response to this constant lunar illumination. Primitive marine organisms, for instance, were sensitive to light. Photosynthetic microbes likely responded not only to the sun's daylight, but to the moon's reflected glow. Though the intensity was weaker than direct sunlight, the moon's light penetrated shallow tidal pools and coastal waters, influencing metabolic activity and daily cycles. Microbial communities may have timed their division, growth, or movement according to these subtle lunar cues. In this way, the moon became an invisible regulator of biology. Beyond microbial life, early multicellular organisms also adapted to lunar cycles. Creatures inhabiting coastal tidal zones experienced not only the physical pull of tides, but the illumination of the moon, which dictated feeding, reproduction, and movement. Small motile organisms could use moonlight as a guide to avoid predators or navigate toward food sources. In ecosystems where daytime was dominated by the harsh glare of the young sun, the soft lunar glow offered a nocturnal refuge, a calm, consistent rhythm amid environmental chaos. The moon's influence extended to reproductive behaviors. Even before complex animals emerged, chemical signaling in early life forms was likely sensitive to light cycles. In later evolution, we see clear patterns of lunar timing in reproduction. Corals synchronize spawning with full moons. Certain species of fish and invertebrates migrate or breed according to lunar phases, and sea turtles use moonlight to find nesting beaches. This biological dependency on lunar light echoes a time when the moon dominated the night sky, guiding the behavior of life in a way no other celestial body could. Lunar illumination also affected predator-prey dynamics. In the earliest oceans and coastal regions, many tiny organisms relied on concealment to survive. A full, close moon could expose them to predators, forcing behavioral adaptations. Perhaps some sought shelter in sediments, under rocks, or in shallow pools that shielded them from bright lunar light. Predators, conversely, could exploit this illumination, hunting more efficiently. These interactions introduced selective pressures, driving early evolutionary innovations in mobility, camouflage, and sensory perception. Even atmospheric chemistry was subtly influenced by the moon's light. On early Earth, ultraviolet radiation from the young sun could break down molecules in shallow waters. Lunar light, by extending soft illumination into the night, allowed chemical reactions to continue in the absence of direct sunlight, providing an extended window for photochemistry that may have contributed to the formation of prebiotic molecules. In effect, the moon extended the productive hours of Earth's early chemistry, turning nights into another laboratory for life's beginnings. Terrestrial environments were not exempt from the moon's influence. Even tiny patches of exposed land during low tides received lunar illumination, which could guide early colonization by algae, fungi, or other primitive organisms. Moist soil, tidal flats, and newly exposed rocks became sites of chemical and biological activity under the gentle glow of a massive moon. These illuminated niches may have been among the first footholds for life outside the water. The moon's brilliance also shaped the evolution of sensory organs. Organisms that could detect faint light had advantages: better navigation, predator avoidance, and feeding efficiency. This may have been an evolutionary driver for early photoreceptors, setting the stage for the development of complex eyes millions of years later. Even today, animals with nocturnal habits often retain sensitivities that trace back to these early interactions with lunar light. Interestingly, the moon's effect on night length and intensity influenced circadian rhythms. Modern humans, with their 24-hour cycles, inherit timing mechanisms shaped by both the sun and moon. Primitive life, exposed to the moon's powerful illumination, may have adapted internal biological clocks to anticipate not only day and night, but also phases of the moon. These rhythms ensured that life was synchronized with environmental cycles, increasing survival and reproductive success. As the moon gradually drifted outward over billions of years, its illumination softened. Nights became darker, tidal effects moderated, and ecosystems adapted to longer, more predictable cycles of light and darkness. Yet the imprint of its early brightness remains, encoded in biological rhythms, reproductive timing, and behavioral patterns across countless species. To imagine this ancient world is to see a landscape bathed in perpetual twilight, where the moon's presence dominates the sky. Oceans surge and retreat under its gravitational pull, Primitive creatures crawl and swim beneath its light. Tidal pools glimmer and glisten, reflecting an enormous lunar orb overhead. The moon is no longer merely a satellite. It is a guiding force, a clock and a lantern, illuminating the first steps of life in a world that is otherwise dark and dangerous. Even today, when we gaze at a full moon, we are witnessing a distant echo of that ancient brilliance, a light that once shaped biology itself. Every nocturnal rhythm, every moonlit spawning, every tidal adaptation is a living memory of a time when the moon's light reigned supreme. Section 11. The Moon and Earth's Climate, How a Close Companion Shaped Weather and Seasons. While the moon's pull on tides and its glow at night are visible and easily imagined, its influence on Earth's climate is far subtler, but no less profound. In the ancient era, when the moon orbited much closer to our planet, its gravitational tug worked not only on oceans, but on the very axis of Earth itself, stabilizing rotation, moderating seasonal extremes, and shaping weather patterns in ways that set the stage for life to thrive. Understanding this relationship offers a calm, yet awe-inspiring glimpse into how celestial mechanics influence the intimate details of life on our planet. Earth's axial tilt, the angle between its rotational axis and its orbital plane, is responsible for the seasons. Without the moon, simulations suggest that this tilt could vary dramatically over millions of years, causing erratic climate swings far beyond anything life has had to adapt to. Mars, with its small moons, suffers precisely this fate. Its axis wobbles unpredictably, producing extreme variations in climate over geological timescales. But Earth, thanks to the moon's gravitational pull, enjoys a remarkable stability. Even when the planet was young and volatile, the moon kept the axial tilt relatively consistent, creating predictable seasons and preventing climate chaos. The effect of this stability cannot be overstated. Life, primitive microbial mats, the first multicellular organisms, and later plants and animals, relied on predictable cycles of light, temperature, and tidal exposure. Imagine a tidal flat illuminated by the young moon, the sun rising and setting on a schedule that never varied wildly over thousands of years. The environment provided a dependable rhythm, a scaffolding on which early life could grow, adapt, and evolve without constantly recalibrating for catastrophic climate swings. But the moon's influence on climate extends beyond axial stability. Its close orbit amplified tides, and tides do more than move water. They drive ocean currents and atmospheric patterns. When the moon's gravitational pull created massive tidal surges, energy transferred from the oceans into the atmosphere, influencing wind patterns and storm formation. Stronger tidal forces meant more vigorous mixing of surface waters with deeper, colder layers, which in turn redistributed heat across the planet. This helped prevent extreme temperature gradients and created more uniform climates across large regions. Even early precipitation patterns may have been influenced. As tides lifted vast quantities of seawater inland, evaporation increased, Moist air was carried over continents, creating rainfall patterns in regions that otherwise might have remained arid. In this way, the moon indirectly nurtured ecosystems, supplying water to nascent forests, wetlands, and coastal marshes. It is possible that the moon's proximity even influenced the timing of monsoon cycles, which depend on oceanic heat distribution and the movement of atmospheric masses. The moon's stabilizing effect also extended to longer-term climatic cycles. Over geological timescales, Earth's rotation slowed due to tidal friction. Shorter days in the distant past meant rapid cycles of heating and cooling, while today, longer days allow more moderated temperature changes. By slowing the rotation gradually, the moon softened the intensity of diurnal temperature swings, giving ecosystems the stability needed for life to spread from oceans onto land. In essence, the moon acted as a slow, persistent moderator of climate, allowing complex life to develop without being constantly subjected to catastrophic thermal shocks. Interestingly, the moon may also have influenced glacial cycles. Ice ages are sensitive to small variations in Earth's orbit and axial tilt. The moon's presence stabilizes these orbital mechanics, preventing abrupt swings in ice cover that could threaten life. Without this stabilizing influence, Earth might have experienced more severe ice ages, with glacial periods far harsher than what the fossil record shows. The moon's subtle, persistent tug may have smoothed the climatic roller coaster that allowed life to thrive rather than merely survive. The moon's effect on weather was not purely protective. Massive tides created by its proximity could have amplified coastal storms. Surging seas and wind-driven waves would batter primitive shorelines, redistributing sediments and shaping the landscape. These storm patterns, although violent in scale, created diverse habitats. Shallow lagoons, tidal flats, and estuaries formed in the ebb and flow of these systems, providing safe zones and breeding grounds for the earliest life. In a sense, the moon balanced destruction with creation. Its pull generated chaos in localized regions, while fostering stability on the global scale. Even today, the legacy of the moon's influence on climate is evident. Tidal forces continue to drive ocean currents, which in turn regulate global temperatures and weather patterns. Hurricanes, monsoons, and other atmospheric phenomena are indirectly shaped by oceanic rhythms established long ago when the moon was closer. Every breeze, every rainstorm, every seasonal cycle carries the faint echo of that primordial gravitational dance. To imagine the Earth under the influence of a close moon is to picture a planet of dynamic balance. Oceans rise and fall with enormous force. Wind and weather patterns swirl in harmony with tidal rhythms, and temperature cycles remain predictably stable despite a volatile young sun. On this stage, life begins to experiment, diversify, and evolve, a dance choreographed in part by a satellite glowing like a lantern in the sky. The moon, in this sense, is far more than a passive observer in Earth's history. It is a stabilizer, a regulator, and an unseen force that shaped the climate and weather, providing both the canvas and the tools for life to flourish. Its proximity may have once seemed violent, its influence overwhelming, Yet it was precisely this influence that created the conditions for survival, adaptation, and eventual complexity. Section 12. The Moon's Slow Drift and its Long-Term Effects on Earth. Over billions of years, the Moon has not remained in the same position relative to Earth. Born from a violent impact, it initially orbited extremely close, perhaps only a fraction of its current distance. From that vantage, it was a massive, glowing presence, tugging powerfully on oceans, the crust, and the very rotation of our planet. But the Moon was not fixed in space. Like all celestial bodies, it moved, influenced by the delicate exchange of energy between Earth and itself. This gradual outward drift, occurring at a rate of roughly 3.8 centimeters per year, has had profound consequences for tides, day length, climate, and the evolution of life. When the Moon was near, days on Earth were far shorter, sometimes only 6 hours long. The powerful tidal forces acting on the planet drained rotational energy from Earth, transferring it to the Moon and sending it slowly outward. As the Moon moved away, Earth's rotation gradually slowed, stretching days to the familiar 24-hour cycle we know today. This lengthening of the day had cascading effects. It moderated extreme temperature swings, giving life more stable periods of light and darkness, and allowed ecosystems to evolve with a reliable rhythm. Organisms could anticipate day and night with increasing precision, fine-tuning biological clocks that still echo through circadian rhythms in modern life. The Moon's recession also influenced tides. In its close orbit, tidal ranges were enormous, hundreds of meters in some regions. These tides reshaped coastlines, stirred the oceans, and created dynamic intertidal zones that nurtured the earliest life. As the Moon drifted outward, tidal forces gradually weakened. This shift created a more stable coastal environment, allowing ecosystems to expand, adapt, and diversify. Estuaries, tidal flats, and shallow lagoons became hotspots for evolutionary experimentation. Animals and plants began to move beyond these transitional zones, gradually colonizing deeper ocean regions and eventually terrestrial landscapes. This slow lunar drift also affected Earth's axial stability. While the Moon has always acted as a stabilizing force, its changing distance subtly altered the degree of that influence. Early in its history, the Moon's close proximity exerted strong torque on Earth's rotational axis, helping maintain a relatively constant tilt. This prevented catastrophic swings in climate and made seasonal patterns more predictable. As it receded, Earth's tilt gradually became slightly more flexible, but still remarkably stable compared to planets without such a companion. This allowed long-term climatic patterns to persist, offering a foundation for the flourishing of life. Earth's geological activity was also subtly shaped by the Moon's drift. As tidal forces weakened over time, the immense stresses on the crust and mantle that drove early tectonics and volcanism gradually diminished. Volcanic activity became less extreme and more localized, allowing continents to stabilize and oceans to settle into the basins we recognize today. In a sense, the Moon's movement from violent proximity to moderate distance transformed Earth from a restless young planet into a mature, life-sustaining world. The moon's retreat influenced marine environments as well. Tidal energy drove strong mixing of surface and deep waters when the moon was close. But as it moved away, ocean circulation patterns adjusted. This allowed for more stratification in some areas, creating diverse niches for marine organisms. The modern balance between nutrient-rich upwellings and calmer, stable waters is a direct consequence of this long-term evolution, guided by the moon's gradual drift. Even biological rhythms were affected by this slow migration. Early organisms evolved to match the intense tidal cycles created by a close moon. As those cycles softened, life had to adapt to longer, gentler rhythms. Corals, tidal invertebrates, and coastal algae adjusted their reproductive and metabolic cycles to the new conditions. Terrestrial life also benefited. More predictable tides, moderated climates, and a longer day-night cycle allowed early plants and animals to establish stable life patterns on land. Interestingly, the moon's outward journey has left an observable signature in the fossil record. Ancient tidal rhythmites, sedimentary layers formed by repeated tidal cycles, reveal that days were once significantly shorter, confirming models of lunar recession. By studying these layers, scientists can reconstruct not only Earth's rotational history, but also the moon's distance over hundreds of millions of years. The planet itself records this celestial dance in stone, a slow-motion testament to the gravitational partnership that has endured through deep time. The moon's gradual migration also hints at the delicate balance that makes Earth unique. Too close, and tides and crustal stresses could have been so extreme as to sterilize nascent life. Too far, and axial instability might have made climate chaotic, hindering the development of complex ecosystems. The moon's trajectory, born of violent origins but moderated over billions of years, was ideal for fostering life. It represents a cosmic interplay in which distance, gravity, and time combined to create the conditions for habitability. Even today, the moon continues its slow drift. Every year, it moves farther away by a few centimeters. While imperceptible in a human lifetime, this movement is a quiet, ongoing reminder of the dynamic forces that have shaped our planet for eons. It is a subtle but constant participant in Earth's natural systems, influencing tides, stabilizing rotation, and quietly marking the passage of geological and biological time. As we reflect on the moon's journey from a massive, molten satellite to the calm, luminous orb we see tonight, it is clear that life on Earth is inseparable from its presence. The moon's migration transformed chaos into stability, violent tides into gentle rhythms, and a restless young planet into a cradle capable of sustaining the diversity of life we see today. Section 13. The Moon's Legacy, a quiet guardian of Earth's life. By the time the moon reached the orbit we see today, it had already shaped Earth in countless ways. It had sculpted coastlines, driven tides, stabilized the planet's rotation, guided climate, and influenced the earliest rhythms of life. The violent, luminous presence of the moon in Earth's infancy gradually mellowed into the serene, steady companion that has illuminated countless nights. Its legacy is subtle but profound, echoing through geology, biology, and the very fabric of life itself. Even now, billions of years later, the moon quietly governs the tides that nurture marine ecosystems, governs spawning cycles in countless aquatic organisms, and marks the passage of time for terrestrial creatures. Our circadian rhythms, our calendars, and even the cycles of flowering and migration in the natural world retain the imprint of this celestial guardian. The moon is a reminder that Earth is not isolated. It exists within a delicate gravitational partnership that has allowed life to flourish against staggering odds. Its influence on tides continues to moderate the ocean's role in climate, distributing heat, driving currents, and shaping the coastal landscapes that host rich biodiversity. The moon also preserves our rotational stability, preventing extreme axial tilts that could otherwise create devastating climatic swings. In effect, the moon acts as a silent architect, ensuring that the conditions for life remain stable over vast stretches of time. Beyond its physical effects, the moon has inspired the imagination of humans, guiding our myths, calendars, and art. Yet its true wonder lies not just in beauty, but in function. The moon is simultaneously a sculptor of the earth and a custodian of life, an unseen participant in processes that make our planet habitable. Its gravity carved the first tidal pools, its light illuminated the first nocturnal behaviors, and its presence slowed the Earth's rotation to a rhythm in which life could thrive. When we gaze at the moon tonight, we see a serene orb, pale and constant in the sky. But we must remember that it is the product of violent beginnings, of collisions and molten birth, and yet it evolved into a stabilizing, life-giving presence. The contrast between its early chaos and its current calm is mirrored in the story of life itself, a transformation from fragile beginnings into resilience and complexity. Every high tide, every moonlit night, and every biological rhythm carries the whisper of the moon's ancient touch. Its story is intertwined with ours, a continuous, gentle influence spanning billions of years. From shaping coastlines to guiding evolution, the moon has been a partner in Earth's journey, quietly steering it toward the possibility of complex life.